Okay. All right. Okay. So I want to recap some of the concepts we discussed last lecture on how recursive algorithms can do excessive work because they recompute the same quantity again and again. Okay, and the simplest example of that is Fibonacci numbers, where if you write down an algorithm to compute the nth Fibonacci number in the obvious way, you will generate a recursion which runs for a very long time. Okay, and while we know that in fact you can write a very simple piece of code which does very little work, right? And the reason for that is that if you look at the recursion for Fibonacci numbers, you see that the recursion is recomputing the same values again and again and again, right? Exponentially many times, right? While if you remove the recursion and do an iterative algorithm, we can come up with an algorithm that runs in n time to compute the Fibonacci of n, right? That makes sense? Okay. Okay. So basically, dynamic programming is the idea that of taking a recursive algorithm and memoizing it so that you don't recompute the same thing. But that's not what really dynamic programming is about. That's the sort of the mechanics of it. Okay. What dynamic programming really is being able to recognize that a given problem, when you think about it in this way, allows you to come up with an efficient algorithm. Okay. So there are two skills in dynamic programming. One is to say, okay, the mechanical part of the dynamic programming is the part where you take a recursive algorithm and you say, okay, if I suspect that I'm going to generate a lot of same problems again and again, then I should not do the recursion in the obvious way. I should memoize it. That is, in some sense, the mechanical part of it, right? The harder part, which comes with identifying certain simple problems and getting more experience, is to recognize when you see a new problem, it does admit a recursion, which when I memoize would lead to an efficient algorithm. Okay? That's the harder part, right? So there are two different things, and the easier part is what you can see with Fibonacci numbers, because it's easy to see in the Fibonacci case that there are not too many problems and the recursion is creating a lot of extra work for itself. Why is it not hard to see that the number of different problems that Fibonacci creates is small? Why is it not hard to see? What about just the simple description of Fibonacci? Is it really about Fibonacci? What if I gave you some other funky recurrence? T of n is 3tn over 2 plus 5n. Is that any different than Fibonacci? Why not? As far as computation is concerned, not its properties. If I gave you any recurrence of the form t of n is a t of 3n, t of n minus 1 plus t of n minus 2 plus 5. Is it hard to compute that? Why is that? Okay, what is it the syntax of the recurrence helps you understand quickly that you should not do recursion but you should just do iteration? Is that, yeah? Yeah, or if I tell you that, I have a recurrence of the form and you don't understand it because it doesn't look nice, or it's not something that you've seen before. For example, I say, t of n is t of n minus 1 plus t of n over 5 plus, n log n. Suppose I gave you this recurrence with base case, I don't know, t of 1 is 2, and I ask, write a piece of code which will compute t of n for any given n, right? Right, so why would, okay, that's true. If you just write the recursion, I mean, if you write code for this, how would you write a code for this? Your code will take n and it will, what should it do? It should output t of n, right? How would you do it? You could just write the recursion as it is, right? If n equal to 1, output 1, otherwise compute these two and sum them up, add n log n and output it, right? You can easily convert this recurrence into code, right? To compute. But I claim that that's not going to be very efficient because it may generate the same problems again and again, right? But it is sort of should be immediate to see that the number of problems that you care about is only n, right? That's from the syntax, right? Because if I want to evaluate n, it depends only on t of 1 up to t of n minus 1, right? So the number of different problems that I need to think about is only n, right? Yeah? So I shouldn't try to just recompute them again and again, just like Fibonacci now, right? Is that clear that the syntax should immediately tell us that, there are only n problems to worry about, yeah? Because it's just a number, right? Yeah? N depends only on n, 1 to n minus 1, right? Okay, but it's not so obvious when we come to something more structural, and that is the trick that we need to get used to, of how to think when we have more different problems, okay? So to think about that, let's okay, I claim that basically there's a very generic principle, okay? So first let's do something very abstract. Suppose I gave you some recursion. I don't tell you anything about it. There's some code called foo, right? It takes some input x and it does some recursion, right? Foo calls itself, foo x minus 1, foo x. We don't know anything about it, okay? Okay. But here is what I say, right? You know, if I run foo on an input of size n, what will it do? It will create some big recursion, right? I don't know what it is, right? Okay? Yeah? Okay, but I promise you the following, that if you start it on some input of size n, it generates a of n different problems. Potentially, no more than a of n different problems, okay? That means it can generate the same problem again and again, but if I look at which ones are distinct, right? What are the different types of problems, what are the different instances it generates when I run it on x? It's only a of n, okay? And, well, you know, when I call foo of x, what does it do? It does some computation and then calls itself maybe multiple times, right? Recursively, right? Okay, I promise you that the work it does other than calling recursion is b of n. Okay? If I look at a foo, what does it do? It does some computation, it calls itself recursively, it does some more computation, and then it outputs something, right? Okay? I promise you that the amount of work it does in a call of when I give you an input of size n is b of n, and the number of different sub problems it generates in its recursion tree is only a of n. Okay? So if I actually run the recursion, it may actually do a lot of work because it may generate the same problem again and again and again, right? Yeah? But I want to know what happens if we memoize the recursion. That means that, you know, once we compute a value foo of y, we don't recompute it again, we store the value of foo of y, right? And we avoid doing the recomputation again. We recognize that foo of y was done and we don't recompute it. Yeah? Question? Yeah, the size of x is n. See, that's why it's a little trickier, because I'm not telling you that x could be some structure, right? It could be a graph, it could be some string, it could be something. All I'm saying is size is n, that is representation size is n. Okay? Okay, how much work do you think, if we memoize a recursion, how much work do you think we will do? Okay, to give an example, what does Fibonacci do? Fibonacci of n, what does it do? In the case of Fibonacci, what is a of n? No, the number of different problems it generates. It's n, right? Because it doesn't generate more than n different problems, right? Okay, what is b of n? How much work does it do when I call Fibonacci of n other than just calling itself recursively? It just adds two numbers, right? Yeah. So it does constant amount of work other than just calling itself recursively, right? So b of n is 2, right, or constant. So how much work if I just do some blind automatic memoization without knowing anything? What does memoization mean? Whenever I see foo of n, I first check, is it already computed by using some dictionary or something? And then I return it if it is already computed. If it is not, then I compute it. So what does that do? If I do that, every different problem I touch only once, no? I'm not going to touch it more than once, right? Okay. So the total work I do, I claim, will be a of n times b of n. That's it. Yeah? Because I'm not recomputing again and again. All right? Okay, that's the idea that, is an abstract idea. Let's make it more concrete with examples. Okay? That's the idea of dynamic programming. That if you actually have a recursion where you know that you're not going to create too many different problems, you know it somehow because of the structure of the recursion, then by avoiding recomputing, you will get an efficient algorithm. Okay? That's the idea, right? So now the question is, other than Fibonacci, are there any interesting examples where this happens and it is hard to see, right? No. I claim it is true, but it's a little different there because in all those recursions where divide and conquer is there, we don't generate the same problem at all again and again. These recursions are different from, see, merge sort. Okay, look at the recursion tree for merge sort. How does it look like? It has, you cut it into half, cut it into half. Are any two of those problems the same? They're not, because you're working on a different part of the array. They're completely separate. So there's no gain you will get in merge sort if you actually memoize a recursion because you're not doing any recomputation at all. That's the nice thing about divide and conquer recurrences, that they don't do extra work, right? Because they are not recomputing the same thing, while Fibonacci is recomputing the same thing again and again. Okay, there's a fundamental difference between divide and conquer recurrences and other recursions that we generate in these kinds of problems. Not calculation, no, we'll see. We'll see an example. Okay, let's make it concrete. So this is a bit abstract. Okay, so that should be L star. The font didn't work, but let's see the problem. Okay, here is a very simple problem. It is connected to things that we've already seen. Maybe I'll forget about the top part. Let's look at the bottom example. So I give you a language like English, right? And this is a Facebook problem, by the way, that a student who, this was an interview question just in case, right? So I give you a string, right? For some reason, my text got, all the spaces got garbled, right? I mean, all the spaces got removed in my piece of string, right? So I want to know, is this an English sentence, right? Okay, what does it mean, right? What I'm trying to say is, I give a string and I want to ask, can I break up the string into words which belong to English? Yeah? Is that clear, the problem? Yeah? So more abstractly, I'm asking the following question. I give you a language L, and how do I give you the language? I give you a dictionary in the form of a function, right? So what does it do? If I give you a string, it will say, is this string in the language? It will answer yes or no, right? We can do that with English, right? Yeah, we have a dictionary somehow, right? But it could be any language you care about, right? Some language, I don't know what this language is, right? But I have access, I give you access to it via this function. If you give it a string, it will say, is this in the language or not? So that function is string in L, yeah? You can assume you have access to it. Now I give you another string. Now the problem is, I give you a long string and say, is it in the language L star? Okay, what does it mean? What does it mean for a language to be in L star? Yeah, it's a concatenation of multiple things from the language, right? Yeah? So this is a nice problem connected to what we've already seen, right? I don't know the language, but I give you access to the language via this simple function that says, is this string in the language, right? Okay. Now I give you a long string or whatever and say, is this in the English star or is this in language L star? Is the problem clear? Yeah? So can I split the given string into substrings, right, without overlapping, right? Can I partition this so that all of them are in the language, right? Okay, clearly, this is an English star, right? Is this an English sentence? I mean, of course, I'm ignoring punctuation and all that stuff, right? Yeah? Okay, is this in the language? Yeah, you can break it up in multiple ways, right? It's not necessarily a unique way of seeing why it's in the language, right? What about this one? It doesn't look like it's an English star, right? Yeah. Okay. So in this case, you should say yes, yes, no, right? That's your problem, right? Any question on the problem? Simple enough? Yeah. Yeah. No, English is not sigma. English is a language that we think of English.
Yes.
Okay.
So sigma would be A, B, C, D, E, alphabet.
Alphabet. Sigma is alphabet.
Yes. So the combination of many alphabets would be part of the language.
No. English is a subset of sigma star. No, English is a set of words in from the alphabet. Not every word is in English. No, not every string is in English. No, so this is not in English, as far as I know, right? So that's it, right? I'm just using English because it's easy to understand, right? But the problem is abstract. Yeah, is it clear? Okay. So if the language L itself is regular, is an easy problem, right? Because you can do something, right? You can make it regular. The L star is also regular. So how will we solve this problem? If I ask you on the interview, how will you solve this problem, right? Facebook says, no, this is a very key problem because we do it all the time. People forget to put spaces in, right? So how will you solve this problem, right? Well, what would your natural instinct be? Don't worry about efficiency. If I ask you to just solve this problem, what you have to say something to the interview person, right? You can't simply say, right? So it's something, you have to start somewhere, right? But that's not what I want, no? So if you generate all possible substrings, but how do I know that I can split it? Okay. No, you have to be more precise than that, no? What does it mean? That I generate all substrings. Yeah, you can check any substring from I to J, whether it's in the language or not. Yeah. Yeah. Yeah, so you're saying, from I you create, yeah. Yeah, okay. So can you make a recursive algorithm out of it? Yeah. Okay. Oh, be more precise, right? What does it? So it would be nice to explain that in a more formal recursive way, so that we don't use things like we back up. What does it mean, right? The backing up should be explained in a nice recursive way. Okay. So that yeah. So I want, yeah. Okay. Yeah.
I was thinking of that earlier.
Yeah.
She is an addiction.
Yeah.
Stop once you see
No, but so then he has to come back and then, right? Yeah. So okay. So one more before I move on, right? Yeah. Yeah. So I'll stop him, right? I only because I want us to in this course, one of the things I want us to get better at the end of it is to not describe algorithms procedurally. Okay, not that because it is so that it is easier for other people to understand also, right? What we're trying to say. Ideal thing would be recursively a compact description that requires you to say something about when something is a string in the language, right? You have to use the definition of when a string is in the language as a guiding principle to come up with a compact way of convincing somebody that your algorithm is correct. Right? Rather, you see, procedural descriptions tend to be complicated because there are many details that one has to say, right? Yeah, so like you said, tree. I'm sure all of you have the right idea, right? But the description of it is better if you think recursively, right? To understand and convince other people that you're right. Okay. So let me just do it because I mean, partly also because of time. It's good to. I hope you spend a little bit of time. So when it goes back to saying, before we think of an algorithm, we have to think, what does it mean for a string to be in L star? What is our understanding of that? What is the meaning of W being in L star? Can we think about it inductively rather than procedurally as a split? What is our definition of W being in L star? Yeah? Yeah, that's good, right? So that's a clean way of thinking, right? If W is in L star, if there are two base cases to consider. Either the whole W is in the language, then we're done, right? If the string itself is in the language, we're happy. Yeah? If it is not, what is it like? It should consist of a prefix which is in the language followed by a suffix which is in L star. Yeah? Does it make sense? Yeah? So this gives us a very quick and easy recursive algorithm, no? Yeah? What is a recursive algorithm if you understand it this way? How will you give it? Yeah? I claim this is a simple recursive algorithm, right? I want to check, assume that it is stored in an array of size n, right? The string. Either if the entire string is in the language, we are done, right? We say yes. Yeah? If not, what do we need to do? We search over all prefixes, yeah? And check, is this from I equal to 1 to n minus 1, proper prefixes, right? And say, is a string in the language A1 to I the prefix in the language? And if the suffix is in L star, then we accept, right? Yeah? Okay? Agreed? Where is the recursion happening? This one, right? Okay. Yeah? Yes. Oh, that's true. Epsilon is important here. Sorry. Yeah, that was missed. Good catch. Okay. So if n equal to 0, accept, right? Yeah? N equal to 0 is epsilon, right? Okay? L star, yeah, epsilons are important. Yes, good. Yeah. Okay? Does it make sense? Okay. So now what happens? I can run this algorithm, and more importantly, I can convince somebody that this is the correct algorithm. No? Worrying about implementation is a different issue. Okay? Yeah? Okay. What happens if you run this recursion? Okay, let's run it on an example, right? Okay, so let's see an example. Okay, today is why do you think I picked that today? People know that expression. Yeah. Sorry? Yeah, I know. Why today? It's a coincidence. It's Dr. Seuss's birthday today. And I only know it because my kids told me, right? They have something in school, right? So so I thought it'd be fun to put it in there, right? Okay. Okay, so if you run this algorithm SAM, what happens? It should work, okay? No, but what does it do? Okay, so I start with SAM, right? Okay. Is SAM in English? We don't know. First, how many problems does it generate? How many problems does it generate? Huge number of problems, no? Yeah? Does it? Agreed? Okay, so what does it do? It generates, depends on how you want to do it, but it'll generate, right? and okay, so on and so forth, no? Am and one more, right? Okay, and this one will generate what? Again, it will generate many things, right? Yeah. Okay, but is there a pattern to this thing in the sense, if I ask you the question of all this huge number of, if I actually run the recursion, it'll blow up, right? It'll generate. But how many different problems am I generating? What does each of this look like? A suffix of the original string, no? But there are not too many suffixes, no? Yeah? How many suffixes are there? If I have a string of length n, how many suffixes are there? N minus 1 or n if you want proper suffix, right? Okay, so that's it. That's the key observation, right? This recursion, if I actually implement it as it is, it will blow up on me, but I'm not actually generating too many problems. I'm just generating them again and again, right? So if I don't actually evaluate the problem recursively and do a memoization, I should get an efficient algorithm. Okay? All right? How do we see it? Well, my question is how many distinct sub-problems that will generate? You see it because you notice that the recursion is only generating a suffix of the original string, no? Yeah? Do you see that you are generating only the suffix? Okay, is that clear? Okay. Sorry? Because it's I plus 1 to n, no? That means it is the characters from position I plus 1 to n, the string formed by for every I from 1 to n minus 1. See, this is what we did, right? In this example, what did we did? SAMIAM generated the suffix AMIAM, then it also generated MIAM, it generated IAM, because what is the algorithm doing? It is saying, is S a letter in English? Is S a string in English? If S is a string in English and this one is in English star, then I accept, right? I don't know, but I have to check, right? And this is saying is SA in English, and if this is in English star, then I accept, right? Okay, if SAM is in English and IAM is in English star, I accept. One of these has to accept, then I accept, right? Yeah? If not all of them say no, then we say no, this is not in English star, right? Right? But it seems like a lot of work, right? Because it is doing but this guy is only also going to generate I am again. Okay? It's clearly wasteful work, right? But the key is that once we recognize that the number of different things I need to, problems I am generating is small, then I don't have to do the recursion. I can get rid of it. Okay? This seeing is the important thing. Okay? The rest is mechanical, right? But the seeing is the important thing, right? Okay? Okay. So now, to make our life easy and to make pattern matching easy, we use some syntactic sugar to make this a little bit repetitive so that we see again and again the same pattern, right? So we give names, right? Syntax is important to sometimes understand. So after we sort of intuitively see that the number of different subproblems is only n, we can name it in a more compact fashion, okay? What is in compact fashion, which immediately makes us see that the number of problems is small? I'm going to say that, ISL of I is a Boolean, which is 1 if the suffix a, I to n is in L star, 0 otherwise. Okay? Okay? Okay. And there are only how many things I'm interested in? I'm only interested in ISL 1, ISL 2, ISL 3, ISL n, right? So this is immediately clear that I'm only interested in n problems, right? Now if I can write a recursion for this using this terminology, I'm done because I have all the things I need to compute what I want, okay? So how can I write ISL? What is the easy case? ISL n plus 1 is 1. I'll interpret n plus 1 to n as an empty string. Just as a syntactic sugar again, right? What is a string from n plus 1 to n, right? We'll interpret as an empty string just to make a base case easy, okay? So that is a 1 because epsilon is in our language, or L star. When is ISL of I 1? When is the string I to n in English star? if, from our understanding of the recursive code, if and only if there exists a j between I and n plus 1 such that ISL j is 1, that means the suffix j to n is 1, and the prefix I to j minus 1 is in English, right? Okay, but this is not recursion, this is just a subroutine call, right? Okay, and ISL 0 is otherwise. If none of these, if there is no j such j, it is 0, right? And what is it that we want to output? ISL 1, right? What is ISL 1? Is the string 1 to n in English star, right? So why did we do this? What is difference between this code and this notation? It is easy to see because we are using indexes as just a number as opposed to carrying the baggage of A and the I and J and all of that. Just like Fibonacci, this helps us see that there are only n problems of interest. Okay? Okay? It's just seeing. It's no different from this. What we have done is we came up with this recursive code and then we are saying, look, I'm only interested in the suffix. I'm not going to carry the baggage of A and N and all of them along with me to get confused, right? So I'm just going to make it a little bit more compact for myself by defining these problems. Okay? Okay? Right? Okay. Now what have we done, right? You know, we can, once we recognize that the number of problems is small, we need to do one more thing to really make it a proper algorithm. So once we see a recursive algorithm and recognize that the number of problems is small, you could just say, why don't I just use automatic memoization and it'll do well, right? But you can do automatic memoization for any recursion. So automatic means that you use a data structure, right? Whenever I find a thing, you know, use a hash table, dump the problem into a hash table and say if it's already computed, I'll just take the value, otherwise I'll recompute it, right? Non-automatic is what I'm going to do now. Okay, so why do we want non-automatic thing? So that we can strip out the recursion ourselves by hand so that we can further optimize the algorithm if we want and we fully understand the structure of the problem. Okay? That is the idea of dynamic programming. Why? Because you can do optimization, you can reduce running time, you can reduce space and things like that. So first, you know, we need to allocate a data structure ourselves to store all these problems, right? Okay. What do you think should we allocate for this particular problem? If I have a string of size n, how many problems did I generate? N problems, right? Okay. And what are they? We know from this thing that it is ISL 1, ISL 2, ISL 3, ISL up to n, right? So what is the natural data structure to store these things? It's just a Boolean array of size n, right? Okay. So we allocate our data structure ourselves, right? And then we remove the recursion by computing the things bottom up rather than following the recursion. Okay. Let's see how we can do that. Okay. Okay, it is, the iterative algorithm looks like this, right? It's just following the recursion, but we allocate a data structure and remove the recursion. Okay. So what is it? What is the data structure we need? It's an array of size n plus 1 simply because I'm adding this last guy, right? As a sentinel. So is of n plus 1 is true because that's just the epsilon case, right? That's the base case. So for I equal to n down to 1, right? I'm going down now. I start out with it being false. I don't know whether it's true or not. I check for j equal to I plus 1 to n plus 1 if ISL of j and the string a I to j is 1, then I set ISL I equal to true. And finally, if ISL 1 is true, then output yes, otherwise output no. Okay. So let me run this algorithm on SAM-IAM, right? How it works. Okay. So SAM-IAM is what? This string, right? Right. So what it is doing is that it is first starting with this position and saying, you know, is M in English star? How do you check whether M is English star? It's you know, basically it checks whether M is in English, right? Okay, because we follow the recursion, right? When is M in English star? If either in M is in English, or M can be split into M and epsilon, right? But that's the base case. Is M in English? No, I can't split anymore. So the value of at the position here is 0, right? It is not in, the string M itself is not in English star, right? Okay. Okay, now we go here. Is the string AM in English star? Why? How do we think recursively, right? You know, AM is in English star if and only if what? AM is in English, or A is in English and M is in English star, or, right? Okay, those are the three cases, right? So we have to try all those three cases, but how AM is in English, right? Okay, so that's already 1, so we can stop there if you want, right? If you want to optimize. So we say 1, right? What about I am? So that's what the bottom-up recursion is doing. How do you compute I am? I am, so it has to check I am is in English, right? Okay, that is one check, right? It's not, presumably, right? You know, right? And then it has to do what? I is in English and am is in English star, right? Okay, but it already knows the value of am, whether it's in English star or not, right? So it doesn't recompute, it looks in the table, right? Okay, what does the table tell me? 1, right? Good. And then I stop, no? So A is in English, okay, so we can put 1 here. What about MIM? Is MIM, I want to check MIM is in English star or not. What does it do, the algorithm? First it checks whether MIM is itself an English word, is it? Probably not, right? You know, okay, and then it checks, okay, M is in English and IAM is in English star, right? Okay, M is in English, well, it is not in English. IAM, we can check, right, in the table. It doesn't have to recompute, right? Okay, you get the idea, right? No, it checks all of them, right? You know, that's true. No, then you have to check, is MI in English and AM is in English star, right? Okay, agreed? Okay, MI is not in English, so, okay. Okay, is it clear what we're doing? Yeah, and then we fill the table backwards, right? And all the way we come, how does it know that Sam I am is in English? Start. It checks Sam and I am, right? Okay, Sam is in English, I am is in English star. It already pre-computed that, and you look up in the table, so it will check yes. And finally, what is the output? If the last digit is, the last value is 1 or 0, depending on that, we know whether Sam I am is in English. So how much work does this algorithm do if you remove the recursion? Sorry? N is saying, no, I say it does more than N work, right? It does N square work, right? Why? At each step it has to do N checks, no, roughly? Right? It has to split the string and then look up in the table, right? There are N possible splits, no? To check whether Sam I am is in English, and the last step, what does it do? It has to check S am I am, SA am I, right? Right? So for each of those positions, I'm doing N work, no, roughly. And there are N positions, so I'm doing N square work, right? And how much does the tables take? N space. Okay, is the overall algorithm clear? Yeah? Ish? Clear-ish? Is it English? No, the big picture is clear. We started out with the recursive algorithm, very simple recursive algorithm, right? Yeah? And then we realized that if you actually look at the sub-problems it is generating, there are not too many. Yeah? So we can automatically memorize it. It is fine to automatically memorize it, but we want to do better simply because we can optimize this further with data structures and stuff. I'm not going to do it with this problem in particular. But if you know the very simple iterative algorithm, you can use data structures here to speed up the computation. What should I do here in the code optimization wise? What should I have done here? Sorry? I should do break here, right? As soon as I recognize it is true, I should break. Yeah? Agreed? Why am I just looping around, right? Just to make sure that we see that we can, the total work is at most n, right? We just break, yeah? Is it clear? Any questions? Yeah? Okay? Okay. So those are the things, okay. Now we'll do something a little bit more involved in terms of seeing what is going on, okay? Okay. come back to this longest increasing subsequence which we already saw last time, right? Okay, what is the longest increasing subsequence? You remember the problem? I give you a sequence like this, yeah? And you want to find, so let me go there, right? So I give you a sequence like this, and you want to find the longest subsequence, the increasing subsequence, right? What is an increasing subsequence? Here, the sequence where all the numbers are going up, right? Okay, how do we solve this problem? We can again, we do the same thing that we did. We try to solve it recursively, yeah? And then try to remove and understand how much work this recursion would do if we actually memoized it, okay? All right? And what was the recursion we tried? We said, we will break it up into two cases. If I have a long string, a long sequence, how do I find the longest increasing subsequence? Either I want to include the last guy in my sequence or not include it, right? Yes? Agreed? Does that make sense? Yeah? Okay, case 1, if it does not contain the last guy, what do? We recurse on the shorter sequence, no? We break up our sequences into two sets of sequences, those that contain the last guy and those that don't contain it. What is the best solution now among all sequences which don't contain the last guy? We don't know, we recurse on the one less guy, right? Right? If you want to include the last guy, what do we need to do? As we said, we need to throw out everything that is bigger than that, yeah? Agreed? Yeah? No, not clear? How to solve this recursively? I see blank faces. How do we express this problem recursively, right? So to find the longest increasing subsequence in this, either I find the longest increasing subsequence in the first n-1 guys, right? Or I say, okay, I want to include 1, in which case I have to throw out all the guys bigger than 1 and recurse again, right? Yes? Is that, no? That seems a little confusing. Sorry? Okay. Okay. What type of sequences am I interested in? Increasing sequences, no? Yeah, increasing subsequences. I want to find the longest increasing subsequence on this, right? And I want to make the problem a little smaller for myself. Yeah? How will I do it? I say, okay, well, see, the sequence, if it doesn't include the last guy, then I don't have to worry about it, so I can make it a little smaller, no? Right? Yeah? So I say, okay, you can find, recursively find the longest increasing subsequence in the first n-1, and that is one answer, right? Okay? Maybe that's not the right answer, right? Why is it not the right answer? Because maybe we have to include the last guy, right? Okay, but those are only two cases, no? For the last guy. Either it is in my optimal solution or it doesn't. Okay, if it is in my optimal solution, I should worry about that case. Okay, so I say, okay, let's find among all sequences which contain the last guy, what's the longest one? How will I find that? Well, I have to include it. Okay, if I include it, what is the simplification I can do? I can remove everything which is bigger than that, because that cannot be any more, right, in that sequence, right, because this is the last guy. So I drop everything bigger than 1, remove 1 and recurse on the resulting subsequence, right, and find the best one. Either way I make it one smaller, no? Yeah? So that's recursion, right? I made this thing. Okay, that's it, right? Okay, if I write it in the obvious way, the recursion, I claim to you that I will run into a little bit of a problem. What is the problem? The second case, if I take the last guy and drop everything from the bigger than that guy, what do I get? I get something a bit messy, no? What do I get? I get some subsequence of the original sequence, right? It doesn't seem to have that much structure because it could be complicated, right? It depends on the numbers, right? So in fact, you can do that recursion and try to understand, oh, how many different subproblems do I generate? And you will have difficulty in understanding that, okay? Okay, so this is important to understand, okay? The point is that you can come up with a recursive algorithm. For some problems, it will immediately see that the structure of the problem. For other problems, you may get confused, right? So part of the dynamic programming art is to come up with recursions that are simple and clean so that you can see what is going on. Right? Remember, our objective is to understand how many distinct sub-problems am I generating, right? If you make the recursion complicated, that will make your life also complicated. Okay? So to make our life simpler, we will come up with a seemingly slightly more general problem, and that will help us kind of see, right? So okay, here is the slightly general problem that I already discussed. Instead of simply saying I want to find the longest increasing subsequence of a given sequence, now I make the problem a little bigger by introducing one more parameter, another number x. Okay? Now what I'm interested in is the longest increasing subsequence in the given sequence, where I'm constraining you to not use numbers bigger than x in your sequence. Okay? Yeah? Slightly more general problem, right? Okay. So if you have that problem, then it is easy to write a recursion for that. Why? Again, the same idea, right? I have a sequence of length n and now an additional parameter x. This longest sequence either contains the last guy in my sequence or it doesn't, right? If it doesn't, what do I know? I drop it and recurse, no? So one case is I just look at dropping the last guy and recursing. That's the same, right? If I'm not interested in including the last guy, we just drop it and we make the problem smaller, right? Okay, if I want to include the last guy, what should I do? Well, now my problem is slightly more general, no? I can't include the last guy if it is bigger than x, because that's my definition, right? I am not interested in any sequences which are all with numbers bigger than x. So I check if my last guy is bigger than x, I just do the first case. If the last guy is smaller than x, maybe the last guy could be in my sequence, in which case, what should I do? I should include it in my sequence, right? Okay, now again you may think I should throw out everything which is smaller than that guy, right? But I claim something nicer can be done. You recurse on the first n minus 1 guys by replacing x with a of n. Okay, so let me give you an example here. Okay, so I want to solve this problem 6, 3, 5, 2, 7, 8, 1, and I put infinity here. That means that I want to find the longest increasing subsequence in this, subject to the condition that they should all be less than infinity, right? Everybody is less than infinity, right? Right? So how do I solve this? I say, okay, find the longest increasing subsequence in 5, 2, 7, 8, infinity. Yeah? And what else? What is the second case? Maybe I want to include 1 in my solution, right? Okay, but if I want to include 1, what should I do? You might say, I'll throw out everything bigger than 1 and then recurse, right? But that's a little bit clunky, so instead of doing that, I claim we can do the following. I replace infinity by 1, right? So now the new problem is this sequence and followed by 1. Why is that? Because the problem is telling me to find the longest increasing subsequence in this, such that numbers are not bigger than 1, right? So I claim finding these two solutions will give me the solution to this. Yeah? Yeah? Okay. So okay, now let's do one more step so that we understand it's better. What will this guy give, right? Sorry? It will give 6, 3, 5, 2, 7, 1, right? Yeah? And what will this side give me? What will this side give me? Very important. Will I get a second problem here? No, because 8 is bigger than 1, right? I cannot include 8, right? So I won't even get a second problem in this case. Okay? Okay, remember, it will either generate one problem or two problems. Okay? So, but what will this generate? Maybe this is more interesting. What will this generate? 6, 3, 5 to 7 with what? Infinity, that's one case. and 6, 3, 5, 2, 7 with 8 as on case, right? Okay, so I get a long tree, right? Big tree. Is a recursion clear? Yeah? Okay, what is nicer about this recursion? Has anyone spotted what is nicer about this recursion? Yeah. No, you can memorize any recursion. No, not. What does it mean? Yeah. No, something nice is happening. Okay, so let me ask a quick, very precise question. If I start with this array, how many different distinct problems do I generate? Yeah. Why? Why is he able to see it? So what is nice about these arrays that I'm creating? What arrays can I create in this way? Everything is a prefix of the array, no? The first argument has to be a prefix of the array. Yeah? Okay. And what about, so how many choices are there for the prefix? Only n, right? What about the second argument? What values can the second argument take? Sorry? Any value in the array may be, right? But it can't be anything other than infinity or one of the values in my array, no? So how many choices are there for that? Only n, right? So you see that the number of different problems that I generate in this entire recursion, even if I go very far, is only n square. That's the key observation, okay? That you are able to see it only because I change the recursion. See, the recursion is much cleaner here, right? Because it's always generating a prefix. It is not generating an arbitrary subsequence of the array. If you did, then there are too many of those, right? Well, here I am guaranteeing to you that my recursive problems are of the form a prefix of the original array and one of the elements of the array. And that means that there are only n square of them, right? And if you memorize it, doesn't matter, we'll get a polynomial term algorithm, right? Okay, at some level our problem is done, right? We have to do more work to make it a bit cleaner, but that is the important observation, right? You have to see that, there are only n square problems that this recursion will generate, even though I'll generate them again and again and again. Okay, do you see that the importance of seeing that structure, right? It's not enough to solve it recursively. You have to see it in a way that you can understand the problems that you're generating at the bottom or intermediate levels, right? Yeah? Okay, good. It was much easier to see in the other problem. It is a bit harder to see it in here. Again, automatically you can figure this out once you get used to it, but we'll again do a little bit more work to give names, right? Okay, so that it becomes very clear. So I'm going to write LISIJ to be the structure of the subproblem that I generate, right? The two parameters now. What is LIS of ij? The length of the longest increasing sequence in the prefix a1 to I among numbers less than a of j. You see from that subproblem that that's what we're generating, right? Yeah. What is the advantage of giving these names with two parameters? There are only n square possibilities. Okay, we are explicitly realizing that there are only n square problems. So I'll give them names. I and j are indices. And what is the meaning of LIS ij? I look at the prefix a1 to I and say what is the length of the longest increasing subsequence in a1 to I, where all the numbers that I pick have to be less than a of j. Okay? By giving this name, we completely understand that there are only small number of problems, right? Now if you can write a recursion for this, we'll be done, right? Okay? What is a recursion? What is LIS of 0j? What is the meaning of that? That's a base case. The base case is that my prefix is of length 0. It doesn't matter what the j is, right? If I have no sequence, my solution value is 0, right? So LIS of 0j is 0 for all j between 1 and n plus 1. Okay? What is LIS of ij? We saw the recursion, right? LIS of ij is LIS of I minus 1j if a of I is bigger than a of j, right? I can, if I cannot include, why can I not include a of I? I cannot include a of I if a of I is bigger than a of j, right? So then I have to recurse on I minus 1 and j. Yeah? Okay? Remember what is the meaning of LIS of ij? the length of the longest increasing subsequence in 1 to I, right, of numbers less than a of j, right? So if my ith number is bigger than a of j, I cannot include a of I, no, in my sequence. So I can drop it, then I have to recurse on the first I minus 1 and same j, right? There is other case, if a of I is less than a of j, right, I could potentially include it, right? But I don't know which case to try, so I try LIS of I minus 1 j, and if I include that, I recurse on LIS of I minus 1, I replace this with what? A of I now, right? I replace a of j with a of I, right? So that means I replace the j with I. Okay. This is the same recursion, except I am expressing it in a slightly different way. Okay, now this is a two-dimensional recursion, unfortunately. Right? Remember, the problems have this structure that there are I and j, n square problems, no? Not n problems like we saw in the other thing. So it's a little bit more messy, right? Not out of my choice because the problem dictated that, right? Okay, so it is, what do I need to output? I need to output LIS of n plus 1, right? That is the longest increasing sequence of 1 to n with n plus 1 is infinity. That's what I want to output, right? Okay, so you have to write this way, okay? If you don't write this English description, you'll get a 0. I already posted on this, right? Okay, because if you don't understand what you're writing a recursion for, you cannot write a recursion. Okay, I can create whatever I want once you write a recursion, right? So you have to give this, right? It's very important, right? Don't complain later on, right? Okay, just read the rubric carefully, all right? Okay, now the iterative algorithm turns out to be more complicated. Okay, so why is it more complicated? Okay, it's hard to understand. So instead, I'll do a picture. Okay. So what is the data structure we need? Okay, my syntax should tell me what data structure do I need. I need a two-dimensional array now, right? Because my problem is of the form I and j. Yeah, it's not one-dimensional array. My problem is has 2 dimensions, I and j, right? So my data structure should be two-dimensional. Okay, so I allocate an n by n array basically, right? All right? Yeah. Okay, now I have to do bottom-up recursion. Okay, bottom-up iterative computation of the recursion, right? Okay, what do I need to compute? I'm only interested in, remember, this is a little bit careful, I didn't do it initially, but this quantity is defined only for I less than j, not j less than I, right? Because I'm only interested in the prefix and a j which is bigger than that prefix. Okay, so this is what I need to do. What I need to compute is all these quantities, right? I need to compute this, and this is what I want to do. I want to output. Okay, LIS of n plus 1 is what I want to compute. What do I know? What is the base case for me? So I know this row, no? Yeah, all these are what? So I fill that first, right? Okay. Now what should I compute next? Okay, that's to understand that you say, okay, suppose I want to compute something here or somewhere here, what does it depend on? To know the value of this, what do I need to know? You look at the recursion. If I want to know LIS of ij, what do I need to know? I need to know I minus 1, right? I minus 1j. Where is the I minus 1j? The above, right? Yeah? And what else do I need to know in this case? I need to know the guy above, and what else do I need to know? I need this guy, and who else? I also need to know this guy maybe, right? LIS I minus 1, I, right? In the second case, remember LIS of ij in the second case is LIS I minus 1j, LIS of I minus 1i, right? I'm depending on 2 problems, right? Okay, so I claim that if I compute these values in the row order, I will be able to know for every entry all the things it depends on. They will already be computed before me. Is that okay? Okay. If this is confusing, you need to understand two things. You need to understand that this recursion, if I memoize, it will take n square time. Okay, all right. If you're lost in this part, then the rest of it doesn't make any sense. Okay, all right. See, let's recap the dynamic programming. Right, it is a hard concept. I'm not trying to minimize the difficulty of this concept. Right, a recursion can generate many problems again and again. Right. So ideally, we would not want to recompute the same values. Okay, but that's not enough, because we want to know if we memoize the recursion, will it run in what time, right? Okay, because the recursion can take exponential time even if you memoize the recursion. Okay, so there are some cases where if you take a recursion and memoize it, you'll get an efficient algorithm. N square is good, no? It was not clear to you at the start of the day that n square is possible or some polynomial time algorithm is possible, right? Okay, so now we are getting a polynomial time algorithm. This is a kind of a problem where it is not obvious that you can solve it in polynomial time. So how did we see that? We came up with a recursion and then realized that that recursion has a nice feature that if I started on a problem of size n, it generates only n square different problems. Okay, different. I mean, remember, it can generate the same problem a lot of times, but the number of different looking problems is only n square. Okay, and then so from that we can immediately see that if you memoize it, you will get an efficient algorithm. Now there is a second skill which is also important, is that to take that recursion, understand the structure and convert it into an iterative algorithm. Now that's a skill which requires you to understand, what are the problems that I am generating? Well, we already saw that there will be in a two-dimensional array, right? Yeah. Now the second thing you need to understand is that, okay, each of them is a sub-problem of the original problem. How do I order this computation in a way that when I want to fill up this table, I can start at a point and say I have already pre-computed the values that I need. I'll always be able to do it. Why will I always be able to do it? Because it's actually a valid recursive algorithm. Okay, a valid recursive algorithm has a dependency graph, right? Okay, and so if I am at a problem, I should be able to figure out what I need and order the computation in a nice way. Okay, with two-dimensional problems, it gets a little harder. Okay, so I claim that if you compute the values in the row order, whenever you need the values that this guy needs are already pre-computed. Okay, because they are in the previous row, and I've already computed the previous row, and the base case is the first row. Okay, okay, so that's all this iterative code is doing. It is doing it in the row order. You can stare at it later on, right? So why do we do this? Well, some of you may ask, as soon as I realize that the recursion can be automatically memoized, I already have an efficient algorithm. Let's go home. Why are you bothering me with this iterative algorithm, right? Okay, that's a valid point. Yeah, it's a valid point as far as understanding the first order nature of the problem, right? So just to tell you why, let me tell you a couple of questions which will help us maybe address that. I didn't tell you how to compute the solution, right? Suppose I tell you I don't want to know the longest sequence, I also want the sequence. Can you do it? Okay, remember, look at the first problem, is this an English sentence, right? At the end of the algorithm, what do you know? Yes or no, right? But I'm not interested just in knowing yes or no, I want to know the split. Yeah? In addition to knowing that it is an English star, I want to know, give me a proof, or give me the split which will guarantee to me that it's an English star, right? Okay, can you adapt the algorithm to do that? Once you figure out that you found that it is an English star, you can retrace the path of the algorithm, right? And efficiently compute a split that will guarantee to you that yes, that's why I correctly computed it. Okay, efficiently, not right? So that's something you need to worry about. More importantly, you can ask, is there a faster algorithm for longest increasing subsequence, right? And yes, in fact, there is an algorithm which takes only n log n time and O of n space, which is based on a slightly different recursion and then optimized using data structures. Okay. Okay, so that's why we do it, why we remove the recursion, right? Not to know that it's polynomial time solvable. Once we realize it's polynomial time solvable, we can do many tricks by stripping away the recursion. Okay. and you can actually do it in n log n time in n space. Okay, this is taking, how long is this algorithm taking? It's taking n square space in n square time, right? That could be pretty slow for a long sequence, right? But you can do it in n log n time in n space. So that's better. But the way to see it is by removing the recursion, understanding the structure a bit better, and using data structures, right? That's why we do the removal of recursion. Yeah. Okay. These are all important skills because then you see what's going on. Yeah. Okay. Questions. I know that the DP is hard. Okay. Don't. I mean, I'm not trying to minimize the conceptual things involved in understanding DP. Right. Now, there are some people after getting used to this notion of dynamic programming, they'll go directly from the description of the problem to this step, where they don't even go through this all this recursion. They'll immediately see that I can go to this two-dimensional parameterization. Okay, why is that? See, so suppose you suspect that a problem has an efficient algorithm using dynamic programming. You suspect that something like this must be true. So you grope for it, right? It's like knowing a little bit ahead of time that I'm trying to solve it via dynamic programming. If it can be solved by dynamic programming, somehow at the end of the day I have to have a polynomial number of sub-problems, right? How do they look like? Let me see, they either have one parameter or two parameters or three parameters or four parameters or whatever, right? And they kind of intuitively jump to this by using a reasonable definition. So these are called bottom-up thinkers, right? They're like, aha, immediately they can kind of, with experience, guess the structure of the recursive sub-problems, right? It comes with practice. Once you see a bunch of 10 problems on dynamic programming, you will also be good at that, right? So till you get to that point, you have to kind of go slow and understand the steps a little bit slowly, okay? Okay? All right? Questions? Are the conceptual thing okay? Yeah? You see the thing, right? Okay. And so soon you'll be able to recognize that when a new problem comes along, aha, it has a similarity to something that I've seen, so dynamic programming is possible. Okay? Okay. The reason it is very powerful is that it allows you to solve problems in polynomial time, which don't on the face of them look like they can solve in polynomial time. This is very different from divide and conquer, because where the problems are easy to see, right? Here it's not obvious that this can be solved in polynomial. Okay? Yeah? Okay. So we will see more complicated examples. Maybe shall I say one thing about computing solutions? So I mean, maybe this will help you. Okay. Okay. See, when I'm computing these numbers, right? What am I doing? For every suffix I'm calculating, is it an English star or not, right? Can I use some additional? Can I store additional information to compute the split at the end? What do you think I should store additional information? If I tell you all these values, can I go back and recover the split? Yeah? Do you see it? Yeah? Okay, I don't have to explain it. Yeah? If I computed zeros, ones for all the prefixes, and suppose the end is 1, right? Sam, I am is 1. I can output the split Sam, I am efficiently. Yeah, you have to go back to the array, right? How can you do that? Yeah, if you store that zeros and ones, you can go back, no? Yeah. Why did I choose Sam I am is 1? Because Sam was in English and I am was in English star. So I can output Sam as a split and then go and say, oh, now I have to split I am because it's an English star. Why did I conclude I am is in English star? At some point I recognized, right, I plus am is the reason why I, so okay, now I output I and then go to am and is an English star. Why did I conclude am is an English star? Because am was in English, right? So I output am, right? So once I store those values, I can walk backwards to output the solution too, right? And you can do it with any DP problem. Okay, you have to be a little bit clever sometime, but you can do it with any DP problem. Yeah? Once you figure out the value, you can compute the solution also by walking backwards. Yeah? Okay? So that's it. All right. So hopefully you'll get practice with the homework on simple problems so that you see the pattern. Sorry? I actually have some important meeting to go to today, so Today is not the best day to linger, but I have a quick question I can, because I finished a little early today. What do you have?
I just need to go through an algorithm.
Yeah, just go slowly. You know, it's a conceptually nice thing.
For the longest increasing subsequence
Yeah.
algorithm, why don't we just go from the beginning of the array and...
I like both.
Oh, okay. That doesn't matter.
No, so for me, the beginning of the array, it flips everything.
Yeah. Yeah.
It's your taste.
Oh, okay. I thought there was...
Can I ask you a question? So, for the homework question 2, it's almost exactly the same as the one you went through in class, the English word.
Yeah, it is. Yeah, it is just to make
But-
sure that you kind of go. No, the objective is a little different. No?
Yeah, but for the English word, you can directly search in English if the word is in English. But for the palindrome, you have to check if it's a palindrome, and that's ON. So it will be ON cubed, right? There's no way
No,
around.
there's a slight change. You know, I twisted it a little bit.
With the plus K, there must be K.
It's simple. It's similar.
But it will still be ON cubed, right? Because to check if the palindrome is ON,
Yeah.
and the recursion itself is ON squared, the DP itself is ON squared. So that's N cubed.
Yeah.
Right.
Yeah. So, but that's because you are counting. I'm not. I assume in that his English is constant time. That's just an assumption. But that is not as a constant time, right?
Okay. So can we do better than N cubed?
Yeah, you can do better than it.
You can do better than N.
I mean, that's not so important for this problem, but you can pre-compute whether something is for all substrings. You can pre-compute whether it's a palindrome and store it in n square time,
Okay. We pick which problem.
right? And so so then you don't have to recompute it again and again. So that's just a small optimization. We are not looking for that primarily,
Each other is
but we are just giving you practice with simple dynamic. Right? Yeah. Good.
Oh, I was just curious about the algorithms. I thought that you could do it in O of n space just using a simple optimization. Like
Yeah. So I didn't want to say it today, but in fact you can only, because my values depend only on the previous array, the
Yeah.
previous thing.
Yeah.
I actually can get rid of the other arrays also.
Yeah, yeah.
Yeah, you can do that.
Okay.
So that's called space saving
Okay.
optimization.
Yeah, because I was thinking about it and I came up with an iterative way to do it that was O of n squared of O of n space. So yeah.
Yeah, you don't need this. You don't need to store that. Conceptually, it's good to store all of it,
Right.
but you don't
You
need
don't
it.
need to. Okay.
I didn't want to say it right in this lecture just to not overload. I will say it explicitly next lecture when I do edit distance, because there it is. I mean, even here it's intuitive.
Yeah.
So I just didn't want to make that point.
Yeah.
It is very important concern. The only disadvantage of doing that, which again is an issue that will come up, is that if you throw away information, rebuilding a solution becomes difficult.
Yeah. But
Yeah.
you can. I'm pretty sure you can still do it.
No, in fact, there is another recurrence which gives you
Yeah.
n space and n square time,
Yeah.
which is not this recurrence.
Oh, okay.
Okay, and that is what can be optimized to n log n,
Okay.
not this one. Slightly different recurrence.
Yeah, because I think I was doing it a different.
Yeah. So that it used to be on my slides. I removed it because it's overload. You can look. I mean, that's the standard algorithm.
Okay. Yeah.
Right? And that's because it can be optimized.
Yeah. Okay.
Yeah.
But in what case do recursion better than
No, that is not. Recursion, no, dynamic programming is recursion. In divide and conquer, you never recreate the same problem basically, right? Yeah. So you don't have to worry about iteration or removing or the memoization and stuff. But in all the other cases, you want to make sure that you don't store recompute.
okay. So like in the case that you would redo the problem along the path.
No. Let's keep in terminology. Dynamic programming is not about removing memoization. That you can do without thinking at all. Dynamic programming is the realization that the problem can be decomposed in a certain way that such that the resulting algorithm will run more efficiently than just than what the recursion implies. It's a technique. Technique to it is. So that's what I'm trying to carefully distinguish. The technique is to recognize when a problem. See, could not tell. It's only when you could suppose I gave you this problem, the longest increasing subsequence. How do you know that it will there is a efficient way to write a recursion? That if there is a recursion for it, so that after Memoize it will run in an efficient time. It's not obvious, no? That recognition is dynamic programming. So, okay, this problem admits a recursion which, when memoized, would lead to a nice structure is dynamic programming. Identifying the structure of the subproblems is dynamic programming. So that is okay. See, well, soon you'll see problems and say, now I see, well, that's dynamic programming. So what does it mean? It means that you have learned the skill to recognize that, this class of problems, if I apply this technique, will result in an efficient outcome, which you would not have recognized earlier on without knowing the technique. That's the only thing. Yes. Because any recursion can be memoized, so it doesn't tell us anything. Yeah, any recursion can be memoized. No? The fact that some give an efficient algorithm, some don't, is not obvious. Or rather, when you see a problem, how do you sort of understand that maybe it will admit a dynamic programming? Does it mean that it will lead to an efficient, not just that it can mix recursive? Skill is working.
Like when I said it could be memoized, what I implicitly meant was that you would have a polynomial number.
No, you have to say it precisely. Memoization is not the thing, but.
Yeah.
So I used to.
Everything can be memoized.
Yeah, I used to do another thing. Maybe I'll still post it on.
I had a really good lecture about before that. So, like, it's just a public question. So, in practice, that's a very. Then you're saying that we're increasing our distance from the recursion, right? So, does that mean that you can have?
No, the locations are given.
It's in the same line.
I'll give you some locations, right?
Yeah.
The goal is to choose some subset of this.
Okay, so I mean, this is just a pedantic thing. The question says that you have is the distance. So in theory, this could be right.
But these are ordered.
Okay. So you can just
Give the all in one direction.
all in one direction. Okay, just maybe.
Yeah. Okay, I think then you may.